Welcome to the final session of this conference. It's a great pleasure to introduce Bharathwaj Palvannan, who will talk about ergodic approach to equidistribution result of Ferrero-Washington.
Thanks, Mahesh. Also, thank you to the organizers for the chance to speak, and thank you everyone for sticking to the final talk of the final day of the conference. So this is joint work with Jungwon Lee, who's at Warwick right now. So I'm really afraid of giving this talk because this is the first time I'm trying to venture into ergodic theory. So I feel like if I give this talk to an ergodic theorists, they would dismiss it as very trivial. But maybe Iwasawa theorists would also dismiss it as very trivial. But I hope what that means is that it can come across as a good Friday evening talk. Okay, so just some classical Iwasawa theory. If you have an odd prime number, in the setup of Iwasawa theory, we have this usual tower of field extensions that give you the stoichiometric ZP extension. So you have Q zeta P, Q zeta P square, Q zeta P cube, so on and so forth. And then when you take the union of all of them, I'm just calling it Q zeta P infinity. And this sort of field extension as a property that the Galois group out here is just isomorphic to the p-adic integer ZP. Okay, and in Iwasawa theory, as is classical, at each step, we want to study the class group. At each step, more specifically, we want to study the P part of the class group. And more specifically, I want to study at the nth level, I want to study the P primary part of this class group of Q zeta P to the n. And maybe another point to make out here is that the base field out here is just the rational numbers Q. And Q zeta P over Q is Galois with Galois group Z mod PZ cross. And so that gives us this FP valued or this mod P stoichiometric character. And by Hensel's lemma or whatever, you can think of this Z mod PZ cross sitting inside ZP cross. So we have this omega, which is this mod P stoichiometric character. And then we have this P primary part of the class group, AN. But there's an action of this Galois group of Q zeta P over Q on this class group. And what this character allows you to do, what this action allows you to do is to look at eigencomponents. So just some basic representation theory, you have some abelian group, and then you can divide it up into eigencomponents. And so I'm just denoting ANI to be the omega I eigencomponent of AN. And you can do this for all I between 0 to P minus 2. And so the result that started Iwasawa theory was this sort of asymptotic result on the size of these class groups. So you fix an eigencomponent I between 0 and P minus 2. What Iwasawa proved was that the P part, the size of this class group ANI, which is a power of P, has an asymptotic formula given in the following way. So if you look at the exponent, there is a linear term lambda, there is an exponential term mu, and there's this constant term nu. Okay, so this was sort of like the first main result that sort of kickstarted this subject. And along the way, Iwasawa also made this conjecture in some generality, but in the setup that I'm describing, this conjecture is now a theorem of Ferrero-Washington. So Ferrero-Washington first proved this conjecture for this setup, and Somnath gave an alternative proof. And the conjecture and the theorem is that the invariant mu, the sort of exponential term mu I, is 0. And so maybe I should say that Iwasawa's theorem and this mu equals 0 conjecture, they're both stated. The theorem is true in much more generality. It's true for any ZP extension of a number field. And this conjecture mu equals 0, this is true. This is also conjectured in much greater generality, and it's conjectured for any stoichiometric ZP extension. For for any number field. And this conjecture, as I've stated, for any number field that's open. So this result of Ferrero-Washington and Somnath, they show that this mu invariant is 0 in general for abelian extensions. So what that means is that in general, I can also introduce the same level n. So instead of q zeta p, I can look at q np, q zeta np, q zeta np squared, q zeta np to the n, and so on. So I could introduce this. I could introduce this same level n, but just for simplicity and because the results are a little bit cleaner to state, I'm always going to fix the same level to be 1. Okay, so somehow the sort of motivation, the initial motivation is setting this mu invariant, and just by some sort of basic algebra. So we have this ring. It's called the Iwasawa algebra. So if you look at Gn, which I'm denoting it to be the Galois group of q zeta p to the n over q zeta p, and you can look at this group Gn as n varies from 1 to infinity. And as is typical in Iwasawa theory, we want to look at this completed group ring. So I want to look at this sort of group ring Zp adjoint Gn. There are these various surjective maps, and then I just want to take an inverse limit over all these group rings. And so I'm just denoting that inverse limit as Zp double bracket G infinity. And what Serre showed was that this completed group ring, which is called this Iwasawa algebra. So Serre showed that there's a sort of non-canonical isomorphism between a power series ring in one variable and Zp, this Iwasawa algebra. And the isomorphism goes by sending 1 plus t to some chosen topological generator. Okay. And to sort of link it with the Iwasawa invariants that I mentioned earlier. So these Iwasawa invariants lambda and mu, they can actually be found out by some power series in the Zp double brackets t, and it's this characteristic power series fi of t associated to some Iwasawa module. Okay. And so the question is, when is mu 0 or when is mu positive? And so the way this works is that mu is positive if you have this power series f of t. So it's just a power series in t. All the coefficients are in Zp. And mu is positive if p divides each of the coefficients of this power series. Okay. But you know, but you have Zp double brackets t, and then you can always we want to ask ourselves, when does p divide each coefficient? Which just means if I go mod p, I want to know if that element is 0 or not. So if I look at this isomorphism, another way of stating that is, okay, I have fi of t in this power series ring. I can look at this corresponding element theta in. So if I have fi of t, I have a corresponding element in the Iwasawa algebra, and that's given by some compatible a system of compatible elements theta in. And another way of stating that the mu is positive is that p divides each coefficient of this theta in. So these theta ins are some group ring elements in ZpGn, and mu is positive if p divides each of these coefficients. Okay, so just some sort of elementary observations, sort of kickstart Ferrero-Washington's results. And before I introduce Ferrero-Washington's result, again, I just want to introduce some notations. So for every p-adic integer alpha, you can look at its p-adic expansion. So I'm just writing down the p-adic expansion as the first digit t naught of alpha plus the second digit t1, and then the third digit t2, and so on and so forth. So these digits t and alphas, they belong to the set 0 to p 0, 1, 2 up to p minus 1. And then I also want to consider the partial sum, which just means that I want to truncate it at the nth level. And then if I truncate it at the nth level, I get this partial sum Sn minus 1 of alpha. So it goes all the way up till p to the n minus 1. And so if you look at the partial sum, it's bounded by p to the n. So this partial sum divided by p to the n, it always lies in the interval 0 to 1. Okay. 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 So again, I am interested in figuring out when mu is positive, or when how do I figure out if mu is positive? And sort of the approach is that you have a sequence of compatible elements in the group ring, and mu is positive if and only if p divides each coefficient of that group ring. And so how are we going to get these elements in this group ring? They're going to be this sort of classical Stickelberger elements. So just some more notation. So I'm going to let delta be this Galois group of q zeta p over q, which, as we saw, was isomorphic to z mod pz cross. And then we also have, in general, the Galois group of q zeta p n over q is isomorphic to z mod p to the n z cross. And so it's isomorphic to z mod p to the n z cross. So there's a p part and there's a prime to p part. So I'm calling the p part gn, and I'm calling the prime to p part delta. So this is prime to p, and this is the p primary part. Okay. So, but delta is just isomorphic to z mod pz cross. And so under this isomorphism, identifying the Galois group of q zeta p n over q with z mod pz n cross. So the subgroup delta can be identified with the p minus first roots of unity inside z mod p to the n z cross. Okay, and then we have gn, which is the p part. And so the p part inside z mod p to the n z cross is just a set of all 1 units. So it's everything of the form 1 plus px. Okay, so now the Stickelberger element, there's this very explicit form of the Stickelberger element. So maybe the form that you might have seen is it's this 1 over p to the n summation a times sigma a in this Galois group of q adjoined the Galois group of q zeta p to the n or q. Somewhat traditionally, that's how a Stickelberger element is written. But then again, I'm interested in this question about the mu invariant. So I want to look at power series string. Remember that I want to look at the power series strings, some sort of inverse limit over zp, but the group ring is gn. So I want to separate out the p part. I want to separate out gn. So I want to write the delta part separately, and I want to write the gn part separately. Okay, so now if you just follow our nose, and if you write down the p part separately and the so we have this a in the z mod p to the n z cross. So I just want to write the p part separately and the n part separately. Okay, so when you follow your nose and do that, so we have a sum over gn. We have a sum over the p minus first roots of unity, and each group ring element, I'm just writing it as this group ring element given by eta. That's this p minus first roots of unity, and this group ring element given by gn. Okay, and so we are interested in this Iwasawa module, this inverse limit of class groups, and so the Stickelberger element actually annihilates the minus part of the class group. No. Every element in z mod p to the n z cross is just written as an element in eta, element in delta times element in gn. So it's just, I'm just summing over elements in delta, and then I'm summing over elements in gn. Okay. Yeah, so a compatible system of Stickelberger elements can be used to construct the Kaporo-Leopold p-adic L functions. And so now we are interested in looking at the different eigencomponents for the class group, so what we're interested in doing is we have this delta, and then I want to look at all these various characters of delta into Z mod P Z cross. It sits inside ZP cross. Okay, so all that means is that I have this group ring like element. I have that character. So what I'm essentially doing is I have this group ring element in delta, and I'm just specializing it at the character. Okay, and the way the mod P atomic character works is that if you evaluate omega at this eta, you get eta back. So if I evaluate omega to the I at sigma eta, I get eta to the I. Okay, so that's the sort of simple observation that led to the sort of criteria that's originally due to Iwasawa. Again, I want mu to be positive, which means that I have these group ring like elements. And I just want every coefficient in this group ring like element to be divisible by P. So I wrote down these Stickelberger elements in terms of these partial sums. But then again, if you follow your nose, if you look at the partial sums, the partial sums are also given by these p-adic digits. And so the way Iwasawa wrote down this criteria is that there exists an odd integer between 0 and p minus 2 with this sort of property that this summation eta to the p minus 1, the summation over the p minus first roots of unity of some quantity is congruent to 0 mod p. Okay, so this just comes from the fact that I'm just sending sigma eta to the d. Okay. Okay. But if you, it's a Tian. So I explained something using Sn, but I'm just saying that if you just follow your nose, you can also express it in terms of Tn, and I'm writing it in terms of Tn because Tn is between 0 and p minus 1, and Iwasawa wrote it this way. Yeah, so this sort of criteria is originally due to Iwasawa, but Ferrero-Washington also gave an alternate proof, but using essentially the same idea, or the same approach to prove this. And I said that I want to look at these eigencomponents, all eigencomponents between 0 and p minus 2. But then the second statement is I'm only looking at odd integers between 3 and p minus 2. Okay, so the first statement I is for every integer between 0 and p minus 2. And the second statement is again for all integers between 3 and p minus 2, but only the odd ones. Right, so yes, okay, so that was going to be my next statement. So the restriction to the odd integers comes from an application of the reflection principle. So if you have like so you have this odd component and the even component, and there's this reflection theorem that tells you that a specific even component, the p rank of it is less than or equal to the specific odd component, and that's less than or equal to the specific p. Okay, so so the reflection theorem is something like the p rank is some specific p rank of ai is less than some specific p rank of aj for I even, and here j odd. And so if I remember correct, okay, I don't remember this correctly, but I plus j is
P.
P. Okay, thank you. Yeah. Okay. So, okay, yeah, thank you. Yeah. So if I plus j is P, then there's a sort of relation between the ranks. And so this statement involving the mu invariant follows because if there's a positive mu invariant, then the p rank grows exponentially. And so it's some sort of asymptotic formula where the p rank grows exponentially. So you can't have this eigencomponent having positive mu invariant and all the odd eigencomponents having 0 mu invariant. Okay. Okay. Anyhow, so yeah. So the restriction to the odd integers comes because you can deduce information about this reflected even component using the reflection theorem. But I should also maybe say that since I'm working with the tame level 1 case, this is sort of conjecture or problem. It's called the Van der Waals conjecture that all the even eigencomponents are just 0 on the nose. So this is sort of heuristic or prediction, and it's labeled Van der Waals conjecture that the lambda, mu, and nu invariants are all 0 for even I. Okay, but that's just an aside. Okay, so now I want to mention this equidistribution result of Ferrero-Washington. And again, just going back. So you see that I have this sort of element out here. So the sort of criteria is that I want this element to be not 0 mod p. But this element itself is some sort of sum. So it's this sort of sum over this p minus first roots of unity. So I have a sum of over this p minus first roots of unity, and I really want to say that when I sum this thing, it's not 0 mod p. So these things are between 0 and 1. And sort of the first prediction is that these things are just equidistributed between 0 and 1. Okay, so you have this p minus 1 things, and the sort of hope is that these p minus 1 things are equidistributed in 0 to 1. So that statement, as I've said it, is false. And so there are some restrictions. So there are some restrictions because you have these sort of p minus first roots of unity. If you adjoin the p minus first roots of unity to q, that gives you a Galois extension whose Galois group is the Euler-Taussian function of p minus 1. And the Euler-Taussian function of p minus 1 is actually it's smaller than p minus 1. It's at least half smaller than p minus 1. Okay, all this is to say is that I have this p minus first roots of unity, and there are obvious linear relations between these p minus first roots of unity. Okay, and so because these have some sort of linear relation, they're not linearly, so these p minus first roots of unity are not linearly independent, they are linearly dependent. For example, if you have a p minus first root of unity eta, minus eta is also a p minus first root of unity. But anyhow, so I really want these things to be equidistributed in 0 to 1, but there's like some restriction because these things have some sort of linear dependence. But the sort of insight of Ferrero-Washington is that if you remove the linear, if you keep removing elements till you get a linearly independent set. So once you get a small enough set that's linearly independent, maybe then I can hope for equidistribution. Okay, so that's the sort of setup that they begin with. So they begin with algebraic numbers beta 1 to beta r. So they're algebraic numbers, but I also want to think of them inside ZP with a property that they're linearly independent over Q. Okay. So what we want to consider is, so I guess the Iwasawa's criteria, I wrote it in terms of Tn, but I'm going to write it again in terms of Sn. So I want to look at all these partial sums divided by p to the n. So I want to look at this Sn minus 1 over p to the n. Not of beta 1, but I'm introducing this alpha beta 1. So I have this R. So I have this R tuple in 0 to 1 to the r. So all these partial sums Sn minus 1 over p to the n. Not of beta 1, but alpha beta 1. Not of beta 2, but alpha beta 2. Not of beta r, but alpha beta r. I have all these tuples, and I'm letting n vary. And I'm looking at the set of alpha in ZP with the property that this tuple is equidistributed. Okay, so I want to look at GR as the set of all alpha, where this tuple is equidistributed with the property that this tuple is equidistributed in 0, 1. And so the main result is that if you start off with beta 1 up to beta r being linearly independent over Q, then this set GR has full Haar measure in ZP. Okay, and so this is so Ferrero-Washington have like I think 2 or 3 propositions to get this mu equals 0 statement, and this is one of their main ingredients to prove this mu equals 0. Okay, and so as I mentioned earlier, they apply this proposition to a linearly independent set of p minus first roots of unity. Okay, and so Ferrero-Washington, to deduce this equidistribution statement, they use something called the Weyl criteria on 0, 1 to the r. Okay. And what we want to do is, instead of using this Weyl criteria, we just want to give some sort of alternate approach, which is sort of based in ergodic theory, and it's sort of following ideas of Furstenberg. Okay. So just maybe to review some ergodic theory or ergodic preliminaries. So again, I'm going to start with, I'm always going to assume a lot of things. So if you have a compact space, and so you can look at the Borel sigma algebra, and suppose you have a probability measure on the Borel sigma algebra. So the Borel sigma algebra is just a sigma algebra generated by all the open sets. And then a sequence xn in X is said to be equidistributed when it does the obvious thing that you think it would do. And just to state it a little precisely, what it means is that if you take all continuous functions from this compact topological space to R, the sort of average, the evaluation of this function at all these xn's. So if you evaluate this function at all these xn's and take the average, it gives you the integral of f. Okay, so that's the sort of formal way of defining equidistribution. But if you want to just think of equidistribution in 0, 1, it just means that you have a bunch of points, and the obvious thing, it just equidistributes. Okay, and maybe as a tagline, so this is sort of continuous functions in the picture. This is sort of measure in this picture. So the sort of tagline is that it's a property that involves some interplay between topological properties and measure theoretic properties. Okay, so just a tagline. Okay, and so so the point is here we want to do it. So the way equidistribution is stated is you have to check this condition f. So you have to check this condition for all continuous functions, but maybe sometimes you don't have to check it for all continuous functions. It's enough to check it for a specific class of functions, and that specific class is often called test functions. And so for 0, 1, it turns out that the test functions are very nice. They're exponential functions, and so that's the Weyl criteria, that the following statements are equivalent. So a sequence xn is equidistributed in 0, 1 to the r if and only if you take for every non-zero vector in z to the r, if you look at this test function exponential of 2 pi I v, so the function f of x in the previous slide, I'm just taking it to be the exponential function 2 pi I v. So the integral of this function is 0. And so the Weyl criteria is that it's just enough for you to check it on these test functions. Okay. And so the one advantage of the Weyl criteria is that it's very explicit. So you have this criteria, and if you want to show that a sequence is equidistributed, you just have to apply the Weyl criteria. In the case of Ferrero-Washington, it turns out that it's not too complicated. So it just works out. But usually when you want to show this sort of Weyl criteria works, you have to do a little bit of analysis. And the sort of whole motivation behind our project was we didn't want to do some analysis. Okay, so that was the Weyl criteria. But the sort of idea of Furstenberg, the sort of trying to prove equidistribution results using ergodic theory, So you have a dynamical system, the space X, a map T, and a measure nu. So the map is a self map from X to X, and it's measurable with respect to nu. If you have a dynamical system, what it means is that the measure nu is invariant for this self map T. So what that means is that the measure of every Borel set is also the measure of this inverse image of the Borel set. And the map T's definition, a map T is said to be ergodic if for all Borel sets. So if you have a Borel set with the property that T inverse of B is B on the nose, that can only happen if B has full measure or if B has zero measure. Okay. And a point X is said to be a generic point for this dynamical system if the orbit of the point, so you have X, Tx, T of X, T cube of X, and so on. A point is said to be a generic point if the orbit under this dynamical system is equidistributed. Okay, so this sort of ergodic approach is sort of following Furstenberg. So using the Weyl criteria, you have this very explicit criteria. Here's an example. If you have an irrational number, then if you look at the fractional part of n alpha as n varies, then you can show just by doing some maybe elementary analysis, but just doing some analysis on the nose, you can show that this fractional part of n alpha is equidistributed in 0, 1. But what Furstenberg observed is that if you look at the map rotation by alpha, so if you have 0, 1 to 0, 1, and you just send x to x plus alpha, so this is like the rotation map mod 1. What you can show is that this map is ergodic with respect to the standard Borel measure, but it's actually something stronger is true that this map is what's called uniquely ergodic. And so it turns out that every point, if you have a uniquely ergodic map, it turns out that every point is generic with respect to this rotation. So now, if you just look at the orbit of a point x under this rotation by alpha is just x plus n alpha. So if you just look, in particular, if you just look at the orbit of 0, you just get n alpha back again. So every point is generic. So the orbit of 0 in particular should be equidistributed, and the orbit of 0 under this rotation by alpha map is just n alpha. Okay, so this is the sort of prototype that we want to follow. We just want to show that there's an ergodic map, and the equidistributed sequence that Ferrero-Washington had comes from the orbit of an ergodic map. Okay, so here the point is, again, you use these exponential test functions, but then you don't have to do any analysis.
Yeah, hello. Yes. Yeah, what do you mean by generic? The point in interval?
Yeah, so a point is said to be generic if the orbit of that point under T is equidistributed. Yeah, so a point is generic for the map. So I can look at x, tx, t squared, t of x, t of x. I'm just applying t to that point. I get a sequence, and that sequence is equidistributed under the definition I wrote earlier.
Okay.
Okay, I didn't want to say that, but it's a property that allows me to deduce. So what it means is that there's only one measure for which this map is ergodic, and that's the standard Borel measure. So it's yeah. Okay, yeah. So okay, in general, though, ergodic maps are not necessarily uniquely ergodic, and in general, even if you have an ergodic point, not every point will be a generic point. Okay, but then we have this sort of folklore theorem in ergodic theory that if you do have a map between, if you have this self map on compact, if you have this sort of dynamical system, and it turns out to be ergodic, then what you know is that the set of generic points has full measure. So nu is this probability measure, and the set of generic points has full measure. So the sort of upshot of trying to use this theorem is that if I have Weyl criteria, and if I want to show that a particular point is generic, then I can use the Weyl criteria. But maybe that's difficult in practice. And so some sort of theorem like this will come in handy if you want to, if you don't want any specific statement, but you're okay with having this sort of less specific statement, that you have this, that the set of generic points, the set of elements that are equidistributed have full measure. So if you're okay with a less specific statement and just having some full measure statement, some theorem like this might come in handy. Yeah, so for this, all you need is that for a compact topological space, you have a countable set of functions that separate points. So you just have to use Stone-Weierstrass, and for Stone-Weierstrass, you have to cook up this sort of algebra. And so all you need is that you have this countable. Yeah, it's just like very generic, very general. It's just for compact topological spaces. Okay, yeah, so that's our main motivation, is to follow Furstenberg and try to prove some equidistribution results using orbits of ergodic maps. And again, one of our motivations is there's already been applications of ergodic tools to Iwasawa theory, and most notable of which are Kono and Watsal, who independently used Ratner's theorems to prove some results in anti-cyclotomic Iwasawa theory. And again, so the sort of main advantage that we wanted to keep in mind is that trying to use this approach, we can avoid doing any explicit analysis using test functions. Okay. So anyway, our eventual maybe long-term goal is to look at more general situations. So we really wanted to see if it can be applied in a situation where it's already known. So maybe I'm saying a lot of things that are not applicable here, but yeah, our motivation is that we don't want to do any explicit analysis. Okay, so I want to talk about Bernoulli shifts, which are also some ergodic tools. So if you have, so the way this works is that if you have some sort of alphabet space, A1 up to AN, and then you have some sort of probability vector V1 up to Vn. So it's a probability vector. So the Vi sum up to 1. So here it should be A. So the probability measure define. So the probability vector defines a probability measure on A. So A occurs with probability V1, A2 occurs with probability V2, and so on and so forth. And so for this sort of Bernoulli shift, we want to consider one-sided sequence or two-sided sequence of words, and the alphabet of the words are given by elements in A. So it's A to the Z or A to the N. And then we just equip this space sigma with the product topology and the product measure nu on the Borel sigma algebra. Okay, and so now the dynamical system that we want to consider on sigma is as follows. So if I have a two-sided sequence, so this is just, I'm just putting a marker out here. I'm just putting a marker out here to denote the index 0. So I'm just going to consider left shifts. So if I have this two-sided sequence, I'm going to shift everything to the left. So that's all I'm doing out here. So it's a left shift. So I'm just shifting everything to the left. And even if I have a one-sided Bernoulli shift, again, I'm doing the same thing. I'm just shifting everything to the left. Okay, so that's a Bernoulli shift. Okay, on this dynamical system. But I can also do the same thing instead of considering one copy of sigma, I can consider R copies of sigma and again consider Bernoulli shifts. And again, a folklore theorem is that this sort of dynamical system on this R copies of sigma, given by this R copies of left shift, it's an ergodic map. Okay. And out here itself, I just want to sort of make this point that earlier on, I sort of constructed this, or I was talking about this simple ergodic map given by rotation by this irrational number alpha. And I said that map was ergodic. But there's actually not a very nice ergodic map. So if you look at an R4 product of this rotation by alpha map, the R4 product in general, if you take R bigger than 1, it's not going to be ergodic. Okay. So already I just want to make this point that this Bernoulli shift with these sort of symbols, it's an ergodic map, and it has this property that if you take any R4 product, it's still ergodic. Okay, so how are these Bernoulli shifts going to come up for us? The sort of if you go back, I was talking about these digits 0 to p minus 1. And so that's going to be my alphabet space, 0 to p minus 1. And now maybe let me look at a one-sided shift, 0 to p minus 1. And just for simplicity, I'll always consider the uniform probability vector, 1 over p, 1 over p, 1 over p, 1 over p, and so on. Okay. And so if you have this sigma, if you have this alphabet space 0 up to p minus 1, you know, so there's an isomorphism between, so maybe star equals 1, sorry. Just 1. So there's an isomorphism between sigma and zp, where if you have the sequence of elements between 0 up to p minus 1, you just send it to the p-adic expansion of the element in zp. Okay, and again we have the shift map, which was this left shift map, and a p-adic number beta is called normal if it is generic, if it's a generic point for this shift map. Okay, and in general, if you have an R tuple, it's said to be jointly normal. So instead of a one-fold, instead of this map and just sigma, you can look at an R-fold product. And so an R tuple is called jointly normal if that is a generic point for t to the R. Okay, and again, but you know, we're looking at p-adic expansions of zp, but also if you take an integer between 0 and 1, that also has some sort of expansion involving p, and that's the base p expansion. And just like this sort of shift map, you also have the multiplication map on 0, 1, multiplication by p. So you can send x to p x mod 1. But this map is also ergodic. And one way again to see that is if you look at expansions in base p, and if you multiply by p, that's again a left shift. Okay, and I will talk about this a little later. But again, so if you look at Wikipedia or something, which was the thing I did, so the generic points of the multiplication by p map for 0, 1, these are also called normal numbers, but in base p. Okay, and again, if I give you a specific base and maybe combinatorially, you can sort of artificially construct these normal numbers, construct a normal number. So maybe it's possible to give artificial examples of normal numbers. And just as a side point, rational numbers won't be ever normal. But again, this sort of point that if I give you a specific irrational number, it seems hard to figure out if it's normal or not. And honestly, I don't know how hard this is, but if I look at Wikipedia, it says that if you take square root 2, and if you take the base 10 expansion, I don't know if it's known whether square root 2 is normal in base 10 or something.
Known. It's not known. In fact, there's no algebraic number that's known to be normal, although it's conjectured that all irrational algebraic numbers are normal in all bases.
Thank you. Okay, yeah, so okay, it seems hard to figure out if a number is normal or not. And again, maybe here's a hearsay comment that I heard from Ralph Greenberg. And so maybe it goes back to this sort of comment. So before Ferrero-Washington were before they gave their proof, they were giving this talk. And I think Washington and Ferrero independently had some results on the sort of mu invariant. And so if you look at this proposition, you have the sort of final statement is a measure 1 statement. And there's this sort of extra parameter alpha coming into the picture. So this sort of extra parameter is partial sum Sn alpha beta 1 over Pn dot dot Sn alpha beta R over P to the n. But I think this is actually thanks to Rajan who pointed this out. But one of the first approaches was, okay, they were just trying to see, can they just show that if you have a linearly independent set of P minus first roots of unity, beta 1 up to beta R, initially they were just trying to show that that's jointly normal. And yeah, so that I think was turning out to be really difficult. So Ralph Greenberg's suggestion was maybe you can introduce this parameter alpha, and maybe that's enough to get the trick done, get the job done. Okay, so that was Ralph's, I think, observational contribution. And so apparently Larry Washington gave a talk. where they didn't prove mu equals 0, and then Ralph made the suggestion. And apparently, next day, Larry Washington solved it. Okay. And the sort of maybe a very naive observation, but the sort of thing that kickstarts the sort of Bernoulli shift approach is that you have a map from the p-adic numbers to 0, 1, where you send the p-adic expansion to a base p expansion. If you have summation a n p n, you send it to a n over p to the n plus 1. You're sending a p-adic expansion to a base p expansion. And so if you have a map from the p-adic expansion to the base p expansion, this map is continuous and it's also surjective. Okay. Unfortunately, the other way around is not true, but this map is continuous and surjective. So it's actually 1-to-1, except at rational numbers of the form, except at rational numbers that have denominator power of p. And those rational numbers have 2 base p expansion. That's because p minus 1 over p plus p minus 1 over p squared plus dot 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 p minus 1 over p to the n. If you have p minus 1, p minus 1, p minus 1, p minus 1, that adds up to 1. Sort of geometric series. But these are things you might have seen it in topology or real analysis. So instead of sending a thing from base p to p-adic expansions to base p expansions, if you look at the map from the 2-adic expansion to the base 3 expansion, and then you just insert like this 2 here. So if you have a 2-adic expansion, the Tn's, the digits are always 0 and 1. So now if you look at the base 3 expansion, all my digits are 0 or 1. And so if I include this 2, then all my digits are 0 or 2. So this map from Z2 to 0, 1, where you send a 2-adic expansion to a base 3 expansion, essentially, this gives you the Cantor set. Okay, so this sort of maps may look weird, but we have already seen these sort of maps in real analysis. Okay, so maybe, so this sort of motivates us to look at this. So we want to look at 0, 1, and I'm just going to write that as R mod Z. And so the sort of object that I want to look at is sort of a p-adic extension of this circle. So it's just, instead of R mod Z, I'm just going to look at ZP cross R mod Z. And then you can sort of check directly that using p-adic expansions that it's isomorphic to QP cross R mod Z1 over P. And so this sort of p-adic extension is called the p-adic solenoid. And it's a group, it's a compact group. And so you can equip it with the probability Haar measure. And so just like for modular curves, you have fundamental domains. So even for this sort of p-adic expansion, you have a fundamental domain. So ZP cross 0, 1 is the choice of fundamental domain for this p-adic solenoid. And what that means again is that, again, you can check that the natural map from ZP cross 0, 1 to this p-adic solenoid is a surjection. And once you remove the boundary, so the boundary is just 0 and 1. So the boundary is just ZP cross 0, 1. And so once you remove the boundary, you get a homeomorphism. Okay, and again, this sort of fundamental domain, we can also equip it with a measure. So you put the usual Haar measure here, and you put the standard Borel measure here. Okay, so we have the p-adic solenoid. We have this sort of fundamental domain, ZP cross 0, 1. And then using these sort of p-adic expansions and these base p expansions, you have a map from this sort of Bernoulli shift space. So the alphabets are 0 to p minus 1 to the z. And then we can look at the p-adic expansion and the base p expansion. So if you have A0, A1, so on, I can look at the p-adic expansion. And then if you have these negative indices, you can look at the base p expansion. So now from this sort of Bernoulli shift space, you have the surjection onto ZP cross 0, 1. Okay. And again, as we did earlier, this Bernoulli shift space, we equip it with a probability measure corresponding to the uniform probability vector 1 over P, 1 over P, 1 over P. Okay. And so now so on this sort of Bernoulli shift space, I know what the ergodic map that I want to look at. The ergodic map that I want to look at on the alphabet space is just this shift map. So how does it act on the other spaces that I mentioned? So on the p-adic solenoid, again, it's just very simple. It's just multiplying by 1 over P. So if I have like an element X in QP and an element R in element Y in R, this map is just 1 over P. And then if you look at how it works for ZP cross 0, 1. So if I have a p-adic expansion, and then I want to sort of shift things, so then I get A1 plus A2P plus A3P square and so on. That just means I'm removing the first digit and dividing by P. I'm just removing the first digit and dividing by P. And so similarly on the 0, 1 side, I'm dividing by P and then adding this digit. So I'm just adding the digit T naught over X, T naught, Y plus T naught over P. Okay, so we have this 1 over P map on the p-adic solenoid, the sort of skew product map on this ZP cross 0, 1. This is sort of skew because this map on the second part depends on the map, the first part. And we have the two-sided shift map on this Bernoulli shift space. And then I produce all these maps between all these objects, and this sort of dynamical system here, the dynamical system here, the dynamical system here, it's compatible with respect to all these maps. Okay, so we have this two-sided shift on this Bernoulli shift space, this sort of skew product map on ZP cross 0, 1, and then you have this very simple 1 over P map on this R4 product. And again, if you just follow your notes, all these spaces are measurably isomorphic. So if you remove a measure 0 set, they become isomorphic. And what that means is that what's known in ergodic theory is that the top map is ergodic. So that descends onto an ergodic map everywhere. So the skew product map is ergodic. This 1 over P map is also ergodic. Okay. And another point to make is that we have this sort of skew product map on ZP cross 0, 1. But then we also have this projection onto ZP. And on ZP is just a one-sided shift. Okay, so again, the sort of statement that we want to prove is that so eventually we want to get some equidistribution in 0, 1. But this sort of ergodic map comes from a map on ZP. Okay, so somehow we want to shift, we want to get information on 0, 1 by something on ZP. And so we look at this intermediate object, ZP cross 0, 1. And so in this intermediate object, ZP cross 0, 1, we have this skew product map. And I want to look at the generic points for this skew product map. And so suppose I have gamma x1, gamma 2, x2, dot, 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 gamma r, xr in this, this product space. And it happens to be a generic point. The result is that it's generic if and only if so the point is that for every choice of x, this is generic. But it turns out that you can just choose any x that you want. So I've just chosen it to be 0. So this first statement, for every x, x1 up to xr, in this R tuple, this sort of complicated R tuple is a generic point if and only if for a specific point 0, 0, 0, 0, 0. I can choose anything in 0, 1 to the R. I'm just choosing 0, 0, 0, 0, 0. If this one point is a generic point. Okay. And then, so this sort of ZP part out here, gamma 1, gamma 2, dot, 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 gamma r, I can project it down and get a map on this one-sided shift. And so these two statements are just equivalent to saying that this R tuple is a generic point for the one-sided shift. And all this works because it's just a one-sided shift. It's this left shift. So just sort of combinatorially, maybe it might be easy to visualize this. So if you have this sort of big sequence and it's a left shift, what we want is that we want to know how do blocks appear. And so it's a left shift. So if some sort of block appears here, because you're shifting it to the left, it will eventually appear somewhere on the left. Okay, so the sort of genericity for this, okay, I'm just sort of giving you a vague idea, but the sort of genericity for this space only depends on this side, the p-adic side. Okay, so again, we want to establish some relation on 0, 1 using some information about ZP, and this sort of intermediate space is ZP cross 0, 1. And then notice that if you want to look at this point gamma 1, comma 0, gamma 2, comma 0, dot, 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 gamma r to the 0, and then if you look at the orbit of this point, then the set that you get is something in ZP. So you're just shifting it n times. If you're shifting it n times, you're just removing the partial sum. So you're just removing gamma minus this partial sum Sn divided by p to the n. And then you're sending that partial sum divided by p to the n onto the real side. So you get Sn over p to the n. So you're just shifting these things out here. But then if you notice these Sn over p to the n's, those were exactly the sort of things that came in Ferrero-Washington. And so the observation is that if you have gamma 1, comma 0 up to gamma r, comma 0, and that's a generic point, then this set that I wrote down is equidistributed. But then the map from ZP cross 0, 1 to 0, 1, that's a continuous map. And it sends, and the natural measure out here sends it to the standard Borel measure. And so what that means is that if you have an equidistributed sequence, so what that means is that if you have an equidistributed sequence on the left-hand side, and if you push it down, the projection of that set, which is this set out here, that's also going to be equidistributed in 0, 1 to the r. It's just a continuous map that preserves measures. Okay, but the one property, so the one obstacle for us for a long time was that you have an R-fold product, and we wanted to reduce the R-fold product to the case 1. And we really tried to do this using symbolic dynamics, and we couldn't do it. But then when we come back to the p-adic solenoid, the map was very simple. The map was just 1 over p. And then just this observation that if you take any non-zero vector in z to the r, you have a map from r copies of the p-adic solenoid to 1 copy of a p-adic solenoid just by taking the linear combinations. So if you have an R-fold copy, you can just take a linear combination. But then it's just a simple map multiplication by 1 over p. And so this sort of diagram commutes. Okay, so essentially using this diagram, what we can conclude is that if you have gamma 1 up to gamma r, that's a generic point for the one-sided shift. If and only for every non-zero vector, the linear combination m1 gamma 1, m2 gamma 2 up to mr gamma r is a generic point for the one-sided shift. So somehow this allows us to go from the general R case to the one-dimensional case. Okay, and so these were the two propositions that we had to prove, and the Ferrero-Washington equidistribution result can be deduced from those two propositions. And so the linear independence of the beta i's comes in this reduction step from the general R case to the R equals 1 case. So we were looking at these linear combinations, and that's where the linear combinations of the beta i's came into play. And the other sort of measure theoretic fact that we needed to use was, so the linear combinations were combinations in z to the r, which is a countable set. And so you had to use the fact that a countable intersection of full measure sets had full measure. And so the sort of thing that we wanted to observe was that the reduction step from a general R to R equals 1, that was just something purely group theoretic. There was no explicit analysis involved. And so what we observed, I think, was that the sort of ergodic nature of the situation was all encapsulated in the R equals 1 situation. Okay. So I think this is maybe my final slide. Yeah, so I just want to maybe say a lot of vague things to sort of say why we were motivated by this project. And so the sort of eventual goal is to consider generalizations. And so there are lots of generalizations. Yeah, whatever I'm saying is just like vague nonsense, but I just want to say it anyway. So ideally, we would like to consider generalizations. So if you just want to look at mu invariants, there are all these sort of open questions about totally real number fields, elliptic curves, and modular forms. And even the case of real quadratic fields, that itself, I think, will be interesting. And instead of R mod Z, some sort of GL2 generalization. Just like the elliptic curves and modular forms, which would also be some sort of GL2 generalization. And so if you stick to the case of elliptic curves and modular forms, this sort of Stickelberger elements are there, and these are constructed using these modular symbols. And so you can ask, is there an analog of Iwasawa's criteria? And so there is an analog of Iwasawa's criteria, and it goes back to the thesis of Hae-Sang-Sun. And so, like, are there analogs of this sort of equidistribution results? And there are some sort of conjecture results. There are some sort of equidistribution conjectures due to Mazur, Rubin, and Stein. And I think it's not known right now. This analog of Ferrero-Washington is not known, but what's known is some sort of average version of those equidistribution conjectures due to Petridis and Risager, and then Lee and Jungwon Lee and Hae-Sang-Sun also proved it later. And again, maybe the last thing that I want to emphasize is I think our observation in our work was that there was this connection to symbolic dynamics, this sort of 0, 1, this sort of digits 0, 1 to p minus 1. And again, in the GL2 situation, again, there's a lot of connection to symbolic dynamics that goes back to continued fractions. And so there's a sort of relation between continued fractions and geodesic flows on modular curves. And so the goal is like maybe there are ergodic tools to study geodesics on modular curves. And again, like maybe all these questions about mu invariants and ergodic results are all going to be very hard. But the sort of simple question that I want to ask is, we have this Bernoulli shift map, which was ergodic. So what are the sort of, in general situations, what are candidates for ergodic maps? Okay, so that's, yeah, that's my talk.
Okay, let's thank Bharat for the nice talk. Are there any questions, comments?
Yeah, of course, yes. Yeah. So somehow the whole thing starts off because you have very explicit description. You think that's like an equidistribution statement? I thought it's more, okay, my impression was that, yeah, sorry, yeah. Yeah, I mean, for me, so somehow we have this R-fold product, and as you vary these denominators, for me, Ferrero-Washington is something like, okay, so you have this vector space fp to the r, and you have these elements, and these elements are equidistributed in fp to the r. But for me, C0 was just that every element in fp to the r gets mapped. That's my interpretation of C0's proof. So maybe that's incorrect, but yeah, my sort of vague interpretation was that, yeah, C0's proof was somehow giving us, you have this vector space and you have all these elements, and you want to know if every element, yeah, for mu equals 0, all you need to know is that if every element in that vector space is hit. And I think C0 gives us that. And just that Ferrero-Washington gives us the strongest statement that you have this sequence of elements and it hits every element in this vector space fp to the r in a uniform way. Sorry. Come up in class field theory. Yeah, probably.
Is there some connection, or you can you interpret it from that sense? Where does the solenoid come from?
I know, I don't know actually. Yeah, so the question was, these sort of p-adic solenoids come up in class field theory, and is there a more conceptual reason as to why this come up? I don't know. Yeah, we just tried reproving this and we just saw that this worked, and I really don't have anything more conceptual to say.
I have one question. So what are the objects that appear in this Maser-Rubinstein conjecture? Where, I mean, what is the space where something is equidistributed?
Yeah, so you can look at this modular symbols, phi f. So it's the sort of integral of f of z dz from, let's say, infinity. So there you have this Sn of, so it's just some rational numbers. So x over rational numbers with p part denominators. And so you maybe have to take the plus part and then you have to normalize it with something. So you get something integral, and once you get something integral, you can go mod p. And then you can just ask if these are equidistributed mod p. As take it all. As you, yeah, so somehow, yeah, so it's more precise than this. You fix an n. So for me, the denominators are p to the n, but they work with any denominator. And you look at all rationals x over n, where x and n are co-prime, and then you ask this question. But the sort of results of Petridis, Rizager, Lee, and Sun was that if you fix an n, you really need x over n, but they look at all fractions a over b, where b is between 1 and n, and a is between 0 and b, and things like that. So it's a much larger set, and they prove, yeah. So they call it an average version of the conjecture, but it's over a larger set.
Okay, thanks.
Okay, so I don't understand their method, so I just put a word that I also don't understand. Yeah, so somehow I think the point is, so in this work of Jungwon Lee and Haesang Sun, they use this continued fractions. So they use something to deduce information about this modular form f, but their analysis actually, so you have to do a lot of things, and then eventually the analysis boils down to something that doesn't depend on f. But okay, I don't understand Petridis Sagar to make any claim. Yeah.
Any other questions? Okay, if not, let's thank Bharat again, and we'll start at 5:30.